Okay, we're recording. Thank you. So let's just take a look at the schedule really quick. So today's Friday. You've got your Elm lab due tomorrow. How's it going? Any questions that we want to talk about? I take that as a no. So good. Hopefully that means that you're all having fun and that it's that you're enjoying it and that it's pretty straightforward. Remember, this is the first time we've run this particular lab, so we'd love any feedback that you might have about it. Okay, so today we're going to be talking about applicative or eager evaluation versus normal or lazy evaluation. And we'll talk about why that's okay and how it gives rise to languages like Haskell. And then we'll do some live coding as I introduce you to the Haskell language. So let's just look at the schedule really quick. It's pretty amazing, but we really only got 2.5 weeks of classes left. We'll be finishing up Haskell throughout most of next week, and then we'll segue into quite a few, just like a variety of languages and ideas from programming languages that I think are important and interesting, but rather kind of a mixed bag, a little potpourri of things. Okay, so let me start by introducing you to something called the Church-Rosser theorem. Church-Rosser theorem, here's a pretty good little Wikipedia article on it, which I think also does a good job of, like, the picture I think basically says it all. I wish I had like a more, actually, you know what I'm going to do? Hold on just a second. Okay, we're going to do this. Okay, can everybody see that still? So I've decided to do the zoom in a little bit thing here. So the Church-Rosser theorem, oops, that's not what I wanted. Okay. Church-Rosser theorem basically formalizes the idea that in a functional language, the order of evaluation doesn't matter, of the order of evaluation of different expressions. And in particular, let me just bring up like an empty file here. Okay, here we go. Got a little Emacs thing here. So if we have some function f, and we have some complicated expression for one parameter, and we have some other complicated expression for another parameter, we look at this little function and we think about how we evaluate it. In this class, we've always evaluated expressions like this in a very specific order, which is what's called applicative order, or call by value order. And this is the sort of the standard way that we've always done it. And what you can think of, we can sort of imagine that what we do is we always sort of evaluate, or sometimes it's called rewriting. We rewrite or evaluate the innermost occurrence of a function application first. So what is the innermost occurrence of a function application? Let's give one more example here. So the innermost occurrence is this thing right here. So we would evaluate the innermost occurrence, so we evaluate that. Then we'd look at what the next innermost occurrence is, which is either that or that. We would evaluate both of those, and then we would evaluate the next occurrence, which is this thing, the f. We would evaluate that expression, we get the closure of the function back, and then we would go ahead and evaluate the application, the function application. Okay, so by rewriting the innermost application first, we get what's called greedy or eager evaluation. And this is what we've always talked about. This is what we've always done. But you can also do it, but remember I said order doesn't matter. That's what the Church-Rosser theorem says. And so if order doesn't matter, what that means is we could actually evaluate this thing first, this f, get the closure, And then we could evaluate the function application next. And in fact, in lazy evaluation order, we always rewrite the leftmost occurrence of a function application. So we always sort of evaluate the leftmost thing that we need to. And in that way, we like drill down inside the functions and we just keep evaluating sort of left, 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 left until we actually need to go to the next thing over. And we just keep evaluating this way. Church-Rosser says, it doesn't matter which way we do it, we get to the same place. So if we look at sort of the picture here, you know, I think of it's pretty clear. You start at A, and you've sort of got these two operators, the right operator and the down operator, and it doesn't matter if you go right then down or down then right, I think you end up at the same place. Church-Rosser formalizes that intuition. The caveat is that there cannot be any side effects. So if there is side effects, then order matters, and you have to be a little bit careful. So, but if there's different sequences of reductions, all of which have no side effects, then all of those sequences will lead you to the same place. Okay, so this is just a formal way of saying it doesn't matter, but because it doesn't matter, we can delay the evaluation of things until we're sure that we actually need them. And that's where we get lazy languages from. So today, I'd like to take you on a little tour of Haskell and introduce you to some of the syntax and some of the kind of cool things we can do with this. Hold on just a second. I'm gonna arrange some windows for myself here. Of course, as usual, if you have any questions or comments or whatever, please feel free to raise your hand or just use the chat window. All right, so oh, actually, let me say one more thing before we dive into this. So today we're going to be talking a little bit about Haskell. This is all in preparation for your next lab. So if we look at Haskell and laziness, so the idea is you're going to be using Haskell to create various infinite data structures that will calculate infinite lists of primes, but nothing will crash and nothing will go crazy because it's lazily infinite. And so it's going to be kind of fun for you to do. So take a look at this if you'd like. It's going to be pretty straightforward as far as syntax goes. It's going to take a little bit of thinking as far as thinking through how to set it up so that it's infinite and lazy and efficient. It's a really good lab, I think. So let's go ahead and, so that's kind of where we're headed here. So let's go ahead and fire up Haskell. So like other good languages, we've got a little REPL here, and it's a functional language, and you're gonna start seeing, as we get into this, you're gonna say like, oh wow, this really feels like, almost like a combination of everything that we've seen before. And it's true, like a lot of the syntax that we'll see today feels a lot like Elm, feels a lot like Prolog, feels a lot like regular old Haskell. Sorry, regular old Racket. Okay, so talk about the basics first. You've got numbers, you got math, you've got things like addition and subtraction. Division is integer division, sorry, floating point division by default, but you can get integer division if you care. Most people don't. You've got Booleans. So you've got true or false, capital T, capital F. You've got Boolean operations. So not true is false, not false is true. You've got things like equality checks. You've got things like not equal checks. So that means not equal. You got like greater than, less than, all the usual stuff, okay? You got comments. So this will be ignored, things like that. You got strings. This is a string. Strings actually are just lists of characters. So we can always ask what the type of something is by saying :t or :type. So this is saying that the string hello has type list of characters. You've got just single characters like A or B, and you can't use single quotes for strings. That's an error, okay? Single quotes for characters, double quotes for strings. Strings are lists, and lists can be concatenated. So we can do hello, and we can concatenate that with world, and we get hello world. Because it's just a list, we can index into it. So if we have something like the list of characters hello, bang bang is the index into operator. So this will give us the 0th element of the list. Haskell is zero-based indexing. Yay! So 1, 2, 3. Okay, we can like think of it as just a regular old array. We can define variables. So we can let foo be the list 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We can let bar be the list 6, 7, 8, 9, 10. By the way, in your in the REPL, you need to use the keyword let more than if you're just like coding it in like a source code file. Okay, so things that I type in the REPL will generally be equivalent to what you would type, like what you would actually use to code something, except that we'll be using the keyword let a lot more. Okay, so we can define things like foo and bar. Foo is now a list. Bar is now a list. We can also define our own lists. You know, you do whatever you want, but all elements of the list have to be the same type. So we can't do, okay. And, you know, that's because under the hood, Haskell actually has what is widely regarded to be one of the strongest, strictest, some might argue, best type systems of any programming language out there. Like if you want to be serious, if you're serious about types and type systems, Haskell's the place to be. It has a very powerful type inference engine. And so anyway, so okay, so we can create strings. Sorry, we can create strings, we can create lists. And we've got a lot of functions that we're sort of used to now. So for example, foo is 1, 2, 3, 4, 5. Head of foo is 1. And tail of foo, tail is kind of like rest. Will just give us the rest of the list. Notice that this is not a list. You also have the cons operator, which looks like a colon. So if I do 1, 2, 3, 4, that gives me back a list with 4 elements consisting of the numbers 1, 2, 3, 4. Function application just uses spaces. So there's it's kind of like Elm. So we say, that's why we say head foo. There's no parentheses necessary unless you need them to disambiguate something. Okay, good. So those are some of the basics. Let's see a couple of other things about lists. We're going to be doing a lot of examples with lists today, just because I want to get to these infinite data structures, and lists I think are the easiest way to show you that. So Haskell also has a range operator, ... which just takes the first and the last argument and just creates a list with things in between it. So here's the list 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Haskell also lets you specify a step. So 1, 3, ... 10 sort of looks at this pattern, the pattern that I sort of indicate here, and it goes ahead and repeats the pattern until it gets to this stopping place. So in this case, it's skipping every other. By the way, the pattern, this is not like some mystical, like, oh my gosh, it like figures out the pattern. It can do arbitrary patterns. It's not like that. Like if I do 2, 4, 8, 16, ... 256, like it just gets confused. It's just like, I don't know, I don't even know what you meant. All it is you give it the first element and you give it the second element, and it's going to take the difference between those, and it's just going to use that same difference linearly and just apply it. Okay, so it's not like going to do something magical. you can count up or you can count down, but the dot dot operator always, by default, counts up. So if I do 5 dot dot 1, it's going to try to count upwards by 1 until it gets to 1, but that will end immediately, so you just get an empty list. But you can do 5 4 dot dot 1, and you'll get maybe what you expected. So 5 4, and then it'll count down to 1. Hopefully that makes sense. Let me show you just one other function that we'll use a lot today. So we've got our list foo, we've got our list bar. There's also a function called take. So take is a function, you give it an integer and a list, and it will take that many things from this list and just return it as a sublist. So the way I want you to think about take, I want you to think about this very specifically, is take, you give it a number, and then you give it an expression. And it's going to evaluate the first element, like the first entry in that expression, and it's going to put it as part of its list. And then it's going to evaluate the second, put it as part of its list, evaluate the third, put it as part of its list, and it's going to do that n times, okay? So think of take that way. Okay, so we've got head, we've got tail, we've got take, etc. Let me show you one more called zip. So let's remind ourselves foo and bar. Foo is the list 1 through 5, bar is the list 6 through 10. And if we zip foo bar, so what zip does is it takes two lists and it returns a new list. And that new list is, it takes the first element of the first list and the first element of the second list, and it puts them together in a tuple. Then it takes the second element of the first list and the second element of the second list, puts them together in a tuple. Then it takes the third element of the first list and the third element of the second list, puts them together in a tuple, and then it stacks all those things together and creates a new list out of the result, okay? It's called zipping. And you can just sort of imagine you got two lists and we're like sort of zipping them together like a zipper. Okay, so far so good. Like this all feels pretty standard. Looks a lot like Elm, Racket. Like so far we haven't seen anything that feels lazy. So let's do something a little more interesting. One thing that Haskell lets you do is recursive definitions. So I can define a variable in terms of itself. And that's perfectly fine. And the reason you can do that is because the right-hand side, you don't even evaluate the right-hand side of this definition until you actually need it. Remember, Haskell is lazy. So you might say, well, how can it even know what ones is? Ones isn't defined at the moment that we're doing the equals operator. But you gotta just imagine what Haskell is doing is it's saying, oh, let ones equal to, and then there's something on the right-hand side. I'm not even gonna look at that. I'm not even gonna look at that until somebody tells me that I need it. And I haven't told Haskell that I need this ones thing. I've just given it a definition. So a recursive definition is perfectly fine. So what will happen if I press enter? Let ones equal 1 colon 1. So remember, what does the colon do? The colon is like cons, so it'll take a number and it will prepend it to a list. Well, since this is the prepend operator, Haskell is going to do type inference, and it's going to figure out that the thing on the left of the prepend operator has to be like an object, like a number or a string or a character, and the thing on the right has to be a list. So it's the type inference engine is going to infer that ones is a list. And it's going to say, okay, great, ones is a list. So then if I want to cons the digit 1 onto the list called ones, I know the result of this whole thing is going to be a list. So I need to find the first element of this list. Well, what is the first element of this list? And it's going to say, well, ones. Okay, that's an expression. Let's evaluate the first element of the ones expression. So what is ones equal to? Well, the first element of the ones expression is this. So if I just press enter, nothing happens. It's not a type error, it's not a compile error, it's nothing like that. But I've just created an infinite list of ones. So now I can take 5 ones, and what will happen, so remember what happens. What happens is take evaluates the first entry in this expression. What's the first entry in this expression? Well, it's clearly 1. Then it will evaluate the second entry in this expression. What's the second entry? Well, here's the first entry. The second entry is the first entry of this expression, which is 1. What's the third entry? Well, the third entry is the second entry of this expression. What's the second entry of this expression? Well, it's the first entry of this, etc. All right, so this will give me 5 ones, but it will also give me 10 ones, but it will also give me 100 ones, but it will also give me 1,000 ones. Like, no problem. By the way, what happens if we ask for the type of this thing? So remember, Haskell has this super awesome type inference engine. So what it has decided is the following. The expression ones has the type, this type. So for all A, so A here is a type variable. So it's saying for any type variable, num A means as long as A is a number type. So this is called a type constraint. So it's saying this is like there is a specific type here, and what it is, it's a list of things of type A. But A can't be anything. So it knows that A must be a number. So this, it's given us a general type for this list. And it said, well, it's a list of numbers. And sorry, it's a list of things that are of type A, where A is a number. And so what that means is it could be a list of integers, it could be a list of floats, it could be a list of unsigned characters, like unsigned, like uint 8s or whatever. All of those, so it's a slightly more general version of that type. But this is not a list of strings, it's not a list of booleans, etc. So there's a type constraint and then a general type. Okay, so it is correctly inferred for us that this is a list of things of type number, even though it's infinite, which is awesome. Okay, so by the way, you can construct. So there's a question of, well, if I type in foo and it just prints all the elements of foo, and I type bar and I print all the elements of bar, what happens if I just type ones and press enter? Tell me in the chat window what you think. What will happen? Anyone? The universe will explode, says Bethany. That seems very dramatic. That'd be awesome. I mean, it'd be kind of awesome if that was true. Okay, probably just 1,000 ones because that's all that's been evaluated. Well, let's think about what the display thing is doing here. The display thing says, oh, you want, like you type foo, what I'm gonna do is I'm gonna display the contents of foo. What is foo? Foo is a list. How do I display a list? Well, I'm gonna evaluate the first thing in the list and display it, then evaluate the second thing, then evaluate the third thing, and I'm gonna do that until I run out of things to evaluate in the list. So, now what do you think will happen? My finger is hovering over the enter button. Are you ready? Are you ready to find out? What will happen if I press enter? Do I get 1,000 ones? Do I get 1 1? Do I get no ones? Or will the universe explode? No votes at all? Oh, you guys, killing me. 1 1, says Leah. No, not 1 1. So you get an infinite string of ones. So what this is doing is it's saying, well, evaluate the first thing, print it, evaluate the second thing, print it, evaluate the third thing, print it, and just keep going until you run out of things. Well, there is no end to these things. It's kind of like the gospel. There's no end to truth and righteousness, and there's no end to this list of ones. So it's infinite. So we've defined an infinite data structure, and it doesn't evaluate it until it actually needs it. Printing it out counts as needing it. So as soon as it says, hey, I need to print the fifth element of this list, like someone has to actually give me the fifth element because I'm going to actually print it out. Okay, so I think this is pretty neat. By the way, there's another way we can also define this. If we do, we can use the range operator, and if we just don't give it an end, so if I say 1 dot dot and then close brace, I get the same, or sorry, I get a slightly different answer, yeah. Let's do this. So if I do that, I'll get a list of ones. If I just do this, then remember that Haskell's default is just to count by 1. So it'll go 1, then 2, then 3, then 4, then 5, and 6, and I'll get an infinite list of numbers that are ascending. Okay, so let's start having some fun then with infinite lists and infinite data, like infinite data structures. So I'm going to define a variable. It's called 10 down. So 10 down starts at 10, then goes 9, then 8. But notice I put no closing range on here. So it's going to go down to 0, but then it's going to keep going. So it's going to go negative forever. So if I take the first 20 elements of 10 down, then I get 10, 9, 8, 7, 6, blah, blah, all the way down to negative 9. Okay. So now I have, if I take the first 20 things of my ones variable, then I get 20 ones. So now let's define a new thing called ZTO. And this is going to be zip ones 10 down. So I'm calling zip, and I'm giving it 2 arguments. I'm giving it one infinite list here, and I'm giving it another infinite list here. Now, if this was normal, if we were doing this using eager evaluation order, passing an infinite list as a parameter to a function would mean we'd have to evaluate this parameter. And that would be an infinite operation, and it would never finish. And so, but in a lazy language, we can go ahead and call this function, and we can even give it parameters, and we can even assign the result. And none of that do we actually have to look at the parameters. And so we can be lazy about it and defer it. So I can totally define the variable ZTO. And it's perfectly well defined. It's the zip of ones and 10 down. And now, if I actually want to get some of the things from it, I can like say, for example, take 5 from ZTO, and I'll get the first 5 elements. So I'll get the first element from the first list, and the first element from the second list, and then the second element from the first list, and the second element from the second list, third element from the first list, third element from the second list, etc. And it'll zip it all together. Can you use zip recursively? Asked Bethany. I'm not sure exactly what you mean, but we might be able to do something like this. So now, if we take 5 ZTO, so this is an infinitely defined zipped expression, and I'm zipping that up with this, right? So this is just a list of tuples, and this is just a list of integers. And so if I zip those together, I'm going to get a list where the first element is an integer, and the second element is a tuple. And that's exactly what we get. So does that answer your question, Bethany? Oh, let ZTO equals, okay, let's see. Okay, let's see. So let ZTO equal zip ZTO ones. Now this I don't think will work. And the reason is you need a sort of a base case for ZTO. So you have to ask, what is the first element of ZTO? It's zip, and so zip is going to, you're going to ask, okay, I want the first element of the resulting list from this. So you're going to evaluate the first element of this. So it's going to try to get the first element of this and zip it with the first element of this, but the first element of this is not defined. So I'm pretty sure this is going to bail. Yeah. So the reason is, so the reason it worked previously, like when we had But let me show you. Let me show you. So the reason it worked when we did the ones thing is because we had a sort of a base case, like the first digit was defined. But if we did something like the following, then I think that might work. Oh. Oh, you know what I bet it is, actually? Ha. So I don't think this is, I'm not sure this is a logic error, but it is an error, it's a type error. Here's what I think is going on. So what's the first element of the list ZTL? So we want the first element of this list and the first element of this list. What's the first element of this list? Well, it's just the digit 2. What's the first element of this? The digit 1. So therefore, what is the type of this expression? Well, it's going to be a list, and it's going to be a list of tuples. And inside the tuple, you're going to have integers and integers. Okay, now what's the second element? Second element is, well, we get the second element of this. So zip is going to take the second element of this thing and combine it with the second element of this thing. What's the second element of this thing? Well, it's the first element of this thing. What's the first element of this thing? It's a tuple. So now I'm zipping a tuple with an integer, but that's a different type. So the type of the second element of this list is tuple, comma, integer, whereas the type of the first element was integer, comma, integer. So that's why I think that, you see, it's like I expected a type which was just a list of some type, but you gave me a list of tuples. Like, it's getting confused, right? Saying, oh, your type, your list doesn't contain elements of the same type. But Bethany, you are on the right track. So let me show you an example of something that is kind of interesting, that is recursive and infinite and fun. So take a look at this. Everyone just stare at this for a second. And I want you to tell me in the chat window, what is this going to evaluate to? We haven't seen the zip with function yet, but you're smart. I'm sure if you just stare at it, you'll figure out what it's doing. So tell me in the chat window, what is the result of this expression? Daniel thinks it's an array of the fib sequence. Yes, exactly, it is. And let's see if we can all understand why that is. So I'm going to go ahead and I'm just going to rearrange some things on my desktop here for just a second. Dun, dun, dun. All right, so here's our expression. So the expression, let's suppose, oh yeah, so great. First of all, let's see it in action. So here we've got fibs. What happens if we take 20 fibs? We get the Fibonacci sequence. Great. So it's a list of numbers and they're increasing, and it's a Fibonacci sequence. Let's see if we can understand, though, how we got there from here. I think it's useful for us to see this, and to be precise about how exactly it happened. So here we've got the expression. Let's imagine we want, so let's say we say take 20 fibs. So take 20 fibs, and we're gonna print them out. So that means we want to evaluate the first element of this expression and print it out. So what's the first element of this? What's fib sub 0? Well, we're going to go to the right-hand side. What's the first element? Well, it's 0. That's 0. Great, we print it out. Now let's take the second element. So we're going to take the second element. What's the second element? Well, it's just the number 1. So fib sub 1 equals 1. No problem. Now let's take the third element. What's the third element? Well, here's the first element. Here's the second element. So the third element is, well, assuming that this is a list, this will just be, the third element is the first element of this list. Okay, so what's the first element of this list? Well, we haven't seen the zip with function before, but we can kind of imagine what it does. It's kind of like map, but it takes a binary function and two lists. So the binary function we're going to give it is the plus function. The first argument is the fibs list, and the second argument is tail fibs. Easy enough. I mean, this is a recursive definition. So we would like to evaluate the first element of this list. Well, the first element of this list is we take the first element of this. What's the first element of fibs? We already know what it is. It's 0. And we take the first element of tail fibs. What is the first element of tail fibs? Well, tail fibs is the list that starts at 1. And I mean, we're not sure what all the rest of these are, but it doesn't matter. Tail fibs is this list here. So the first element of tail fibs is 1. So this is going to be 0 plus 1 equals 1. Great. Now what is the third element of this? Well, the third element of this is, here's the 0th element, or sorry, here's the first element, here's the second element, third element, fourth element. What's the fourth element? Well, the fourth element is the second element of this thing. So we want the second element of fibs. Second element of fibs is this. Second element of fibs is this, and the second element of tail fibs is this, so we get 1 plus 1 equals 2, and away we go. Okay, so that is how we can define infinite recursive data structures that have some notion of like a little bit of calculation in them. But again, it's all lazy, so nothing gets evaluated until it's actually needed. By the way, in Haskell, we have list comprehensions. So let me just show you a quick example of that so that we can have some fun with it. So here's a list comprehension. So we've seen this in other languages. This list comprehension creates a list. I'm going to evaluate this expression for everything that gets yielded from this right-hand side. So x is going to take on the values 1, 2, 3, 4, 5, and then we're going to evaluate this, and we're going to collect all the results up, and the resulting list will be all of these doubled integers. We can also put conditions on this, so kind of like the guards we saw earlier in class. So this is going to take x to be these values, and it's going to make sure that it passes this guard, and then it's going to evaluate this expression if assuming that everything succeeds, and then collect the results back into this list. All right, so with that in mind, let's just take a quick look at something that I think is kind of fun. Here's a different definition of the Fibonacci sequence using list comprehensions. So this is a list. The first element is 0, the second element is 1. The third element is the first element of this expression, which is a plus b, where a is the first thing that comes out of this, and b is the first thing that comes out of this. Well, what's the first thing that comes out of fibs 2? Well, it's 0. What's the first thing that comes out of tail fibs 2? Well, it's 1. So this expression is 0 plus 1, and that gives us 1, and away we go. So I think that's pretty elegant. Now let's have some fun. And let me give you a slightly more interesting example of this. Take a look at this. See if you can figure out what it's doing. So we're defining a variable called strings. What is in that variable? We have a few minutes left here in class, so take a second, stare at this. You have all the syntax that you need now to understand this. Tell me what is in the strings variable. Like, what is the first element of the strings variable? Probably just guess. Any guesses? A. Bethany guesses A. Let's see. Take one strings. A. Yes. So it's actually the string. It's like it's so strings is a list, and the first element of that list is the string, single A. See how we get there. So strings, it's going to be a list. What's the first element of that list? Well, it's X concatenated with the list of things, with a list containing an A in it. So that's a variable A. Okay, what is X? Well, X is the first thing that comes out of this. What's the first thing that comes out of this? Well, it's empty string. So we're going to take empty string, we're going to concatenate it with a list containing a single thing A. What is A? A is, we're going to take the first thing from A, and that's going to be the character A. So we're going to take empty string, concatenate it with the list consisting of a single character A. In other words, the string single A. So we're going to take empty string, concatenate it with string containing just an A. And the result is an A. So if I take two strings, what will I get? Well, X, so we're going to iterate over all the A's before we take the second X. So we'll get the second thing in this list, which will be character B, which will convert to a string by wrapping it, making it into a list. And we'll concatenate it with the empty string. So we'll get empty string plus B. So if we take 2 from strings, we'll see A, then B. If we take 3, we'll see A, B, C. If we take 26, we'll see A, B, C all the way up to Z. What will we see? What is the 27th entry in the strings data structure? What do you think? Can you guess? We're going to take the, Bethany guesses AA. So we're going to take the second thing in X, and which is what? Well, X is the second thing in X. The first thing in X was this empty string. The second thing in X is the first thing in the strings thing, which is just A, string A. So we're going to take string A, and we're going to, oh, I guess it's 26. And we're going to take string A, whatever the first thing was, which was string A, and we're going to concatenate an A onto it, and we're going to get AA. So yeah, so if we now take, let's say, I don't know, 100 things from strings, what we'll see is we'll see increasingly long strings. And we can take 1,000 things, and we can take 10,000 things, you know, whatever we would like. And it just gives us increasingly long strings. So here's the last thing that I'll show you before we have to wrap up. Here's a function. We're going to define a function called strings less than n. So this is a function that takes a single parameter n. And the result of this function is defined as a function called take while. So you can imagine what take while is. Take, you give it an integer and it takes that many things. Take while will continue to take things until some criterion is met. What's the criteria? Well, we'll pass it a higher order function. So notice that the syntax for the higher order function here looks almost exactly like Elm syntax /x. So this is, it probably means that Elm borrowed it from Haskell, not the other way around. So /x means we're creating an anonymous function, single parameter. The parameter's name is x. The body of the function is the following expression. Length of x must be less than or equal to n. So that's going to return true or false. So we're going to take while this expression returns true, and we're going to take from strings. So now we could do strings less than, and you give me some integer, and I will give you all strings that are less than that integer, whose length is less than that integer. So strings less than 4, I get all of the strings that are less than 4. Boom. There we go. Cool, huh? I think that's amazing. So we can define these infinite data structures. They're defined lazily, not a problem. And we can take those infinite data structures and we can just use them wherever we want. And as long as we don't do anything silly, like try to evaluate the whole list, or try to calculate the length of the list, or anything like that, then we're totally fine. Or in other words, if I say, what is the length of ones? And then it's just going to sit here and it's going to try to count the length by iterating along the list until there's nothing left to iterate. And that will never end. So the length of ones is infinite, but it can't calculate it. Is a list an array or a linked list? I think you should think of lists as linked lists, as far as I know. Good question. Okay, I think that's a great place to stop. Let's go ahead and call it there. Hopefully you all are excited to dive into Haskell and get to know some infinite goodness. So there's a couple of fun things that we'll talk about as to why lazy language is such a good idea, as well as why it's a bad idea. There are some reasons that laziness is really great. There's some reasons that laziness is a pain and probably not what you want. And we'll start talking about that on Monday. For now, we'll call it here. Have a great day and have a great weekend. And we'll see you all on Monday. Take care.